Well, hello guys. Apologies for the technical problems. The meeting got ended after 3 hours because it was intended to be ended in 3 hours, but we're going to continue. So we left off at the topic, a chapter of corrosion. We're going to quickly finish it, do a couple of practice questions, and move on. Okay. So another important uh, topic of the corrosion is the concentration polarization. So concentration polarization is a relationship between over voltage and current density. So you can read about it, guys. I just gave pretty much the equation in case it is being asked you in the final exam. You can read about it in the textbook. Now, the possibility of getting this on the final exam is somewhat low, but just to be safe, please read about it. Know about the existence of this equation. Okay. Well, okay, problem solving. So we're gonna do two questions just to speed up the process. Yeah, I'm gonna start first with the very simple question, which is to write down reactions. Okay, so we need to write down the possible oxidation and reaction, half reactions that occur when magnesium is immersed in each of the following solutions. So we have hydrogen chloride, we have HCl solution containing dissolved oxygen, and in addition also is iron 2 plus. And then we need to identify in which of these solutions would you expect the magnesium to oxidize most rapidly. So I'm going to leave this question up to you guys to figure out, and we're going to do this part. So part A and part E, I rather. So we need to write down the essentially the oxidation and reduction couple in the HCl solution. So in HCl solution, okay, so what are we going to get? We have magnesium that is being oxidized, right? So magnesium, okay? So we know that the magnesium has two electrons being charged in that, okay? So it's ready to react as always, right? So on its own, magnesium can release two electrons which are freely floating in its valence shell, okay? So that's going to be magnesium 2 plus. So that's going to be oxidation reaction, okay? Because we release the electrons. So let's say we pass a current, and this guy's going to release electrons. So it's going to release two electrons. And this is a so-called oxidation reaction. Oxidation reaction. Now, in order to get the things reduced in the HLC um, system, we need essentially to produce reduction reactions. So those two electrons that are going to go somewhere. Now, where they're going to go? We have positively.
Being recorded.
Okay, somebody's recording me. Okay, that's good. Anyway, okay, where did I left? Okay, so we have hydrogen. Okay, that is about to catch some electrons in the reduction reaction, because again, we release these electrons and we need to gain these electrons. And in the system, everything needs to be balanced. And we cannot just release electrons and they're going to go and disappear somewhere. There's nothing that disappears in the universe. We need to convert an energy into heat, into bubbling, into various things. Okay, so in our case, we're going to pass the current through magnesium in the HCl solution, and we're going to get some sort of gases being formed. For example, in the HCl solution, we have hydrogen. That hydrogen is a reactive component, okay? It is the component that is ready to get reduced. So what happens is we have positively charged hydrogen floating in that solution that is about to catch the electrons, okay? So two electrons that's being released from the oxidation reaction, and we're going to form H2. That H2 will probably be gas. Okay, probably. Very much depends on your ambient conditions, blah, blah, blah. But in here, we need to balance our equation, by the way. So we have two electrons, two of this, so we need two hydrogen. Okay, so this is our couple of oxidation and reduction. Okay, so just as an example, okay. Now for part two, basically for part two, it says that we have a dissolved oxygen. Okay, so what's going to change in part two is the first oxidation reaction is going to stay the same, but so oxidation is the same. Oh God, did it just disappear? Oh my God, I hate PDF. I apologize, guys.
This
Anyway,
meeting.
Mg2 plus is sorry, Mg is Mg2 plus two electrons. That's part A. I So that's oxidation reaction. Now for the reduction in part A, we get 2H plus 2 electron minus is equal to H2. It's in a form of gas, probably. Depends on the ambient condition, as I said. That's a reduction. And now for part 2, our oxidation is going to stay the same. So oxidation reaction is the same. Now for the reduction, we're introducing dissolved oxygen. Okay, so basically what's going to happen is we have H plus floating in the solution, ready to react, ready to balance the system out, and we also introduce some oxygen. Okay, so you can also look up really good videos. In some of the corrosion processes, they literally insert like oxygen into the system in order to introduce more sort of like oxygen intake in order to speed up the process of your corrosion. Okay, so each, and then we also have two of the electrons being floating. So this is going to become essentially water. And that water could be in different states, depends on the ambient conditions. Okay, so that's a reduction process. Okay, that's for part 2. So we need to balance the equation out. So make sure you please balance your equation. Okay, so we have H2 that needs to become 2. Okay, we have 2 of O. So this needs to be 2. So now this becomes 4. And this needs to be 4. Okay, so you need to balance it out. And for the third part, basically what's going to happen is um, we also introduce the iron. Okay, so for the when we introduce iron along with the dissolved oxygen and magnesium and all that stuff, basically we're going to have 2 reduction reactions. So the first oxidation reaction stays the same. The first reduction reaction from the previous part, same, because we still have the oxygen being introduced into the system. And the second reduction reaction is going to be as such. We simply have iron being floating in the solution, and we gain 2 electrons being released by the magnesium, and we produce stable iron rust. Okay, so if you ever done your rusting corrosion experiment, you basically use this reaction corrosion, and then you at the end you heat up your solution, vaporize your water, and you're going to be left with rust. It's pretty cool experiment. Anyway, so that's for question 1. I really want to do the question 2. This question 2 is very interesting question to show you guys. Yeah, okay. This is the last question for this chapter, by the way. So, sorry, not question 2. Question 3 is what I wanted to work on. You can work on question 2, guys, on your own. Anyway, so given electrochemical cell is constructed such that one side is a pure nickel. It's a pure nickel electrode is in contact with a solution containing nickel 2 ions at a concentration of 3, whatever that is, moles. The other cell, the other half of the cell, consists of pure iron electrode that is immersed in a solution of iron 2 plus ions, having a concentration of 0.1 moles. So at what temperature will the potential between the 2 electrodes be 0.14 volts? Okay, so let's digest this question. So we have a nickel, we have iron, they form a couple, corrosion is occurring, we have concentration of one in the other. So as soon as you see concentrations, this implies that we're going to use the question of Nernst question, because we're dealing with concentrations and voltages. Okay, so we ought to utilize the Nernst equation. That being said, let's write down what is being given to us. So we have the delta V of the cell, like the entire cell is given as positive 0.14 volts. Then we're given the concentration of nickel in the solution, which is defined as 3 times 10 power negative 3. Then we have iron, 2 plus, is 0.1. And the F, which is our Faraday number, is 96,500 ampere second per mole. And our gas constant is 8.314 joules per kilogram Kelvin. Okay, so These constants are going to be given to you. Also, don't forget we're working in the absolute value of the temperature. So we're going to be using Kelvin, not Celsius. So if you're wondering what the Kelvin, you should know this. 1 Kelvin is, well, I would say temperature of the Kelvin is temperature of Celsius plus 273.15. Okay, Kelvin. So that's how we convert between Celsius and Kelvin. Um, okay, so we're pretty much good to depart from here and figure out the question. So, uh, solution. Okay, I want to write down basically what is going on here. So we have nickel being essentially given up some electrons in the cell of iron. Okay, so this is how you would write down your chemical cell. Okay, sorry, this is just one line. Okay, so basically they all are in one solution, nickel and iron, and then they basically have some sort of chemical things happening in there. Okay, so let's write down the Nernst equation. Nernst equation, it is a very important equation. Please don't crash. Okay, thank you. Nernst equation is delta V cell is equal to delta V O. Oh God, delta V O plus RT over NF multiplied by natural logarithm and the ratio of your nickel concentration divided by the ratio of your iron concentration. Sorry, so we squeezed here. Anyway, so down here. Yeah, that's the Nernst equation, okay? So what are we given? We're given this. We know these constants. I'm going to explain what n is a little bit later. Um, yeah, and then we know the concentrations. So all basically two things that we don't have. We don't have delta VO, delta V naught, and we don't have temperature. Temperature is essentially what we're looking for. Okay, temperature is what we're looking for. So how do we compute delta V naught? Okay, so that's the next part. Delta V naught is the electromotive difference of the elements, not the entire system. So the elements. So we got to utilize the table that I did mention. So when you see nod, okay, 0 in the power, that means that you got to use the elements and their natural susceptibility to give up electrons given some electrical charge being passed through in terms of volts. Okay. So delta V naught is we refer to it as the cathode. It's always the voltage of the cathode minus the voltage of the anode. So please remember that. It's the difference between the cathode and the anode. Okay, so and now let's go to the table and identify. So I'm going to show you how to use the table. Okay, so very important thing. So, okay, what are we given? We have nickel and we have iron. So if you scan the table on electrode reaction, you can find your nickel being situated right here. Okay, so you should take a note that the nickel has the voltage of negative 0.25. Please don't forget about the sign. The sign matters a lot because the table shows you how the elements are essentially susceptible of giving electrons out. Okay, so this is what defines how cathodic or anodic your element is. So for example, there are some elements that are more prominent to corrode than the other ones. Okay, so for example, gold is highly cathodic, so like it's barely corrodes. But if we talk about iron or some chromium or zinc, it's going to very corrode very much. It's a spontaneous process. So whatever is negative is basically is a spontaneous process. Spontaneous process. And this is like non-spontaneous, okay? Anyway, this basically defines anodic cathodic. So when we're talking about nickel and iron, we can see that with respect to each other, iron is anodic, more anodic compared to the nickel. And nickel is cathodic. Okay. And this is more anodic. Okay. But let's say we had copper and nickel. If we had copper, then in our case, copper would be more cathodic and nickel would be anodic. Okay. So it very much depends on what kind of case scenario you have. In our case, we have nickel and iron. So we have this guy, okay, and we have nickel. So the lower you go, the more anodic you are. So iron is below nickel, so we claim that iron is anodic and nickel is cathodic in our cell, in our case. So when we go down, if we took a note of those values of the voltages, okay, so essentially V cathode is going to be our V nickel 2 plus, not, don't forget, and this is going to be our iron 2 plus. So iron compared to nickel is more prompted to corrode, which is kind of true. Iron is very much corrosive, right? So you got to check the table. You got to check the table. So don't forget about the signs. The signs are very important. So you get minus 0.25 minus 0.44. Okay, so if you forget the sign, you're gonna get a little different value. So for us, 0.19 volts. Okay, is the amount of volts that we need to pass through the elements only to sustain some corrosion reaction. But given the concentrations, we got to use Nernst equation. So now that we know delta V naught, we need to compute now temperature. Okay, so um, basically, I might leave it up to you guys to figure it out because it's just a simple process of isolating the variables, etc. I'm just going to give you a couple of things in the process. So delta V cell is 0.14 volts. So sorry, 0.14 volts. This is going to be 0.19 volts. Don't forget your units. Don't forget your units. Plus RT. So N in our case is 2 because that's how many elements we have. We only have 2 elements, nickel and iron. Okay, so NF. That's 2 elements. Times natural logarithm of your concentration. So it's 3, -3, 0.1. So you basically end up with temperature of 331 Kelvin, which is roughly equal to 58, sorry, degrees Celsius. So that's the answer to this question, guys, okay? Yeah, pretty much it. Again, you just simply isolate for T here. It's going to take a little bit of math here, but shouldn't be too bad. Any questions about corrosion? Do you understand oxidation? Do you understand redaction? Do you understand why and how? Some feedback would be appreciated as well.
It's pretty good.
Pretty good. Okay, nice, nice, nice. Yeah. So when you have a corrosion couple, write it down in this way. It's a very sort of like noted way in textbook to do that, but like I don't know, up to you guys. You can just simply use whatever you want. Um, okay. Well, my question to you guys now is I have another set of questions to solve before I go to multiple choice questions. Those are good questions. Um, uh, these are based on the midterm stuff before. 1 second. Yeah, so I have one practice question for the phase diagram, and I have one practice question for diffusion, and I have one practice question for just a chapter 3 stuff. I think we're gonna skip this one. You're gonna get the solution, guys, soon. You can do it on your own. My question to you guys, do you want to do diffusion? Do you want to do phase diagrams, or do you want to just jump into the multiple choice questions? Multiple choice, please. Okay, that's one person. Jump into MC. Okay. Any more feedback? For the ERF question, are we expected to also do the interpolation? So yeah, if you want me to cover this right now, I can do it for you. Like I'm pretty good to cover you, honestly, these 2 problems and then do the multiple choice. But if you want to guys jump into multiple choice, uh, yeah, so you would need to do interpolation if needed. If needed, you need to do interpolation. Okay, I actually expected you guys to say to solve the phase diagram question because I know a lot of people had trouble with the phase diagram, but I guess if not, then it's okay. All right, I guess is that a general consensus? Any more comments? Should I solve? Should I not? If not, then I'm gonna move on to MCs. Okay, one person says phase diagram, another person, please support him. Okay, one says phase diagram. I wish we could do voting, but I'm only one person. Can you do phase diagram? Can you move on to multiple choice question? Okay, well, the phase diagram not going to take much. Going to take about maybe 5-7 minutes. I would definitely recommend you to watch me guys doing that because it's important. And then we're gonna skip diffusion and go to multiple choice question. Okay, that's the decision Okay. All right. Let me get a sip of water and we shall proceed. Okay, so all right, guys. So phase diagram. Okay, so that's the question. You might be given a phase diagram, the diagram itself, and you might be asked to essentially quantify and calculate at various temperatures using the lever rule and tie line the mass fractions. Okay, given that you have lead and tin, 70% and 30%. Well, the first trick that I definitely recommend you guys to be aware of is to first of all be able to orient yourself in the phase diagram. When you're given that there's a 70% of lead and 30% tin, you might just look at it and say, hey, this is my like 70% over here. I'm chilling. Well, that's not true. You need to observe 70% of what? Like, is this take this figure is composition of what? In this figure, it's a composition of tin. Okay. So in our case, we have a composition of tin of 30%. So we actually need to orient ourselves right here. So it's a 30% of tin and 70% of lead. Okay. Even though it says lead here on the left and tin here, you got to take a look at what composition the table represents on the x-axis. For example, when I was working on this yesterday, I was like, usually it's always starts from left. Like the lead is always the composition of that. And I made a mistake. I just put a mark here, like 70% lead. I was like, no, that's not true. Gotta be here. Okay, so be careful about that. Well, that's the first thing. Second thing, the mass fraction of the liquid and per eutectic from. Okay, so we need to calculate. So we know that the metal is being cooled from this point at 300 degrees Celsius at this certain composition. Okay, it's been cooled down to solid state. Okay, so we start from liquid, go from alpha plus L, and then go fully to alpha plus beta. We go to two-phase solid, one-phase solid plus liquid and liquid. That's a regular thing. So, okay, let's figure out our part A. Okay, part A. Sorry, with the momentum. Okay, so just pull up my notes. Well, anyway, so we need to figure out the mass fraction of the liquid and per-eutectic primary alpha at 250 degrees Celsius. So this is 250, incrementally true. This is 250. We pass a horizontal line. Okay, so not really a good horizontal line. One sec. Okay, so this is the 250 Celsius. Okay, so we basically have liquidus line. This is liquidus line, and this is solidus line. So those are our main two boundaries that define the amount of alpha and liquid at a certain composition at a certain temperature. So two parameters, composition and temperature. They kind of sort of like lock down your parameters that you need to work with, okay? So here we need to drop down because the tie line needs to intersect with solidus and liquidus line. So we drop down and figure out what's our composition down here, and we figure out what's our composition down here. Okay, so this is going to be about 33% of tin, and this is going to be about, I'll call it 12% or something. Yeah. Okay, so, and this is our tie line. Basically, we have this tie line, okay, and we have this tie line. So basically, what we're looking at is we're going to solve the question now. Now that we geometrically identified, yes, go ahead. Somebody want to guess something? No? I just heard somebody speaking anyway. Part A, we're going to be quick about it. The mass fraction of the liquid and per-eutectic primary alpha to 50. So we need to find the mass fraction of liquid and solid. So we need to find the W alpha and W liquid. Okay, as soon as we find one of those, it's just one minus the other one and we're done. So for example, omega alpha. So in order to find the amount of solid, we need to essentially find this distance and divide it by the entire distance. Okay, so in terms of the compositions, we know that this is C naught. This is the initial composition. The general equation to that is X L liquid minus, well, I'm gonna call it CL. C liquid minus C naught divided by C liquid minus C alpha. Okay, so this is how we find the mass fraction of, oh God, 1 second, guys, I apologize. Oh, here we go. Sorry, good, deleted a little bit. Just gonna reconstruct it quickly. This is a C naught. This is our CL, and this is C alpha. Again, why C alpha here? That's because it's touching the solidus line. Why CL here is because it's touching the liquidus line. This is 33%, this is 30%, this is 12%. Okay, so at the end, our in part A, our omega alpha is CL minus C naught minus CL over C what alpha. Okay, so basically it's going to be 33 minus 30 divided by 33 minus 12. So we end up with 0.1469, which is about roughly 14.7% of solid. Sorry, yeah, of solid. And the liquid is just simply going to be one minus the other one. So that's going to be about, what's that, 85.3% of liquid. Okay, which makes sense because just by looking at it, we're like at 250, we're very close to the liquidus line. So like we have a lot of liquid, but we're still in the semi-solid state. So this is how you do it. Okay, so for example, for part B, the part B is the mass fraction of the liquid and pre-eutectic alpha just above eutectic temperature, and the weight in kilograms of these phases. So there are two things. We are changing now the temperature to the eutectic temperature, well, above eutectic, that's what they say. So this becomes our tie line now. Okay. So this is above eutectic. This is sort of the concentration that we're concerned about now. Okay, so our C liquid is going to become now 61.9%. And our C alpha is now 18.3 in this case. Are we in part B now, right? Yes, we're in part B right now. Yeah, so part B claims that we need to move on from 250 Celsius now, and we need to obtain the mass fractions at the eutectic or right above the eutectic. So the privilege of eutectic is that we already have the timeline being drawn for us. Basically, that's the timeline, okay? So I just let me cluster it. So this is our C naught. This is going to become our C alpha. And this is C liquid. We're given the values. We're given the initial composition of 30%. So if we are right at basically right slightly above the eutectic line, so we need to find the composition now of our components, of our elements. So the weight fraction of alpha phase is the same equation as we used before, Cl minus C naught, Cl minus C alpha. In this case, our numbers do change. So it's 61.9 minus 30 divided by 61.9 minus 18.3. Okay, and 18.3 is coming from here. It's our solidus composition. Liquidus is coming from this eutectic reaction. So liquidus composition, and our initial composition is 30%. That's what we start with. And the answer to that is 0.853. So it's 85% roughly of solid. Let me plug in my charger. 1 second. And we are back to business. Okay. Okay. So that's 85% of solid, and now liquid is just simply 15% left. Which does make sense if you look at the diagram. Let's say you're like above that line, so you have like a lot of solid now because you're already solidifying, and very small amount of liquid left, but still some good portion of it. So you just need to keep solidifying until you form fully solid solution. Now for the mass fraction, initially you're given that you have 1 kilogram of the substance, okay, 1 kilogram of the alloy. So you basically use the weight fraction to find your mass. What does the primary mean in the question? Okay, so the primary means alpha. Okay, so primary means alpha. Okay, primary means alpha. because that's essentially, so you have, yeah. So you come from two solids and you end up with one solid, or like two different solid structures form into one solid as you move up with the temperature at a certain composition. Okay, so that's what it means. Alpha means primary, beta means like secondary structure. Yeah. Well, as you can see here in part C, we'll need to find alpha and beta. Okay, alpha and beta. So we're going to find that. And so far, in order to find the mass, now to find the mass is very simple. You simply have 1 kilogram. You multiply that by your weight fraction. So if you're looking for the mass of the solid above the eutectic, so that's just times 0.85. So you end up with 850 grams of solid. Now for the liquid, you end up with 150 grams of liquid left. Okay, for part B. That's very simple. For part C, now we need to obtain, so I'm going to remove all of that from here. Okay, we're going to remove all that. Good, good, good. Okay. So now we need to find the weight in kilograms of alpha and beta formed by the eutectic reaction. Is 1 k always our total? In this question, yes, you're given 1 kilogram total. 1 kilogram is what you're given. Uh, okay, hopefully that makes sense. Anyway, yep, no worries. Okay, okay, well, we need to create a timeline. Again, lever rule is the way to succeed in this question. So basically what we need is the weight in kilograms of alpha and beta formed by the eutectic reaction. So we need the eutectic reaction right now. But now we need alpha and beta, not just alpha. Okay, so when we said that we needed alpha before in the part B, we were only concerned about this timeline because this is where we have alpha and liquid being essentially merged, okay? And this is the eutectic reaction. But now we need to compute alpha and beta being formed, okay? So in order to do that, we need to consider the entire timeline over here, the entire timeline. We need to drop our, this is going to be our C alpha. This is going to be our C beta. C beta. And our initial composition, no, we're no longer concerned about initial composition. It's the eutectic reaction. So we're no longer having the composition of 30%. So it's a question that is sort of like asking you, hey, if, let's say you had a eutectic composition, so you would obey the reaction as such, liquid equal to alpha plus beta. So you remember before I showed you the table, but that table is what has the eutectic reaction. That's why I mentioned you need to remember what the eutectic reaction is, okay? So now you're saying that, hey, if I had a eutectic composition of 61.9%, then what would be my alpha and beta in that reaction, coming from fully liquid to two solids? Well, the answer to that question is as such. You're just utilizing the same pretty much equation. You're looking for alpha eutectic. So I'm going to name this as a eutectic alpha, which is going to be your C beta minus C liquid, which is eutectic, over C beta minus C alpha. So what did I just do? I just said that, hey, this is the entirety of the thing, and this is only a portion of it. In order to find alpha, I need to divide this length by this total length. Okay, that's what I said. Well, and the answer to that is going to be 0.452. Okay, so obviously the liquid eutectic. So for the beta eutectic, right, that's going to be basically beta eutectic. Beta eutectic is going to be 0.548. How do you know which timeline to choose? So you read the question very carefully because in part B, so part A is simple. You're given temperature, 250 Celsius, right? So you simply construct your temperature and yeah, and you can define that you're in this region located. So you got to use this region. Now in part B, you're saying, hey, we're right above the eutectic temperature, right above it, and the only thing that we're concerned about is coming from at a given composition of 30% from here. Okay, we're right above it. Okay, so we're about to solidify. Okay, so it's right above the eutectic composition, and the only thing that we're concerned about is the primary composition alpha. Primary. Okay, so we're using the timeline to calculate the primary composition here. Okay. So that's the timeline you would use. But now you're saying that, hey, we have a fully eutectic reaction, so the things are changed now. So we're looking for now for alpha and beta. So you're going to consider this entire timeline from alpha and beta, given that this is now your C liquid. Okay, and now you're concerned about this beta and this alpha. Okay, so yeah, that's how you compute it. And for the mass fractions, well, it's just going to be exactly this. Yeah, so you can calculate, guys, the mass fractions based on this. Well, that is it for this phase diagram question. Please ask me any questions. I would like to move on, obviously, to multiple choice. Yeah. So yeah, no matter how much I try, I always end up with like 4-hour study halls. Oops. Yeah, this is the way. Anyway, any questions, guys? Please unmute or speak or message. If not, then I will conclude the video recording and then I will move on to multiple choice questions. No questions from Pablo. Okay, that's good. If you can all write down the feedback just quickly. Thank you, so we can move on. That'll be good. So we're gonna conclude the meeting. Okay, yeah, for question 2, please solve this. I'm gonna post the solution later today. It's a very good question, so please do it. It has a lot of good things. Try it on your own first, please, because don't just simply copy. You will not understand what's going on. Anyway, all right, in that case, since there are no questions, I would like to conclude the study hall, the portion of it of theory and the practice questions. So thank you very much for attending the study hall. To those of you who are watching on the YouTube, wherever, good luck on your final exam. I believe in you. I only accept A pluses, so please do well. And if you have any questions, this is my email. Okay, you gotta reach me by email. If somebody knows me personally, please feel free to reach me in Discord, blah blah blah. But this is my email. Feel free to utilize it. If there are any issues with the website, please let me know as soon as possible. If there are any issues with the videos, please let me know also as soon as possible. That being said, thank you so much and good luck on your final exam. And